more about mappings. First, I'm going to start with a continuation of this example, and first I have to correct an error from the first one, which was if we plot these 4 points, 1, 0, 0, 1, 1, 1, making a nice little square in the UV plane, what does that do over here in the XY plane? Well, when we put in 0, 0, we get the origin. When we put in 1, 0, we get 1, 1. When we put in 0, 1, we get 1 comma minus 1. So that's going to be down here. I think that was one of my errors. And then when we put in 1, 1, we get 2 comma 0. So it's actually over here. We get a square. It's actually a bit bigger. If you look at the side length, it's root 2. This will be relevant when we talk about the Jacobian determinant, changing variables and integrals, that this has actually doubled the area because the side length has gone up by root 2. So this has area 1, this has area 2. So that's the correct picture of where this square is going. So let me erase that, though, so you can always rewind for that if you want. What's more important often in changing variables, and it's also just really important in understanding transformations in general, is suppose I have a region in XY space. I want to know what region did that come from in U and V. And so let me draw a rectangle here. 1, 0, 0, 1, let's say. Connect those guys. And then I'm going to go up and over to 3, no, this is 2 comma 3. And here's 3 comma 2. And you can check that is really a rectangle. That isn't crucial, although it's going to prove to be particularly simple over here. Okay, so we'd like to, if this call this rectangle R, we'd like to say what is the region that came from. So we want some mystery S over here so that T of S is equal to R. And that's the mystery. Another little more sophisticated way to say it is we're constructing S. There's a notation that it kind of looks like the inverse function notation, but it's actually a little bit different. This means take R and pull it back through the transformation. Kind of like inverting the transformation, but it's just saying all the things over here that end up in R. Okay. And so this is another way to say it. It's all the stuff so that T, when we put in any point in this mystery region S, we get an R. Okay, so let me clear out some space. I want most of this stuff. Okay. I'll put in a little workspace up at the top here. So first thing we want to do is, as I was saying in the first video, is when we're going backwards, we want implicit descriptions. That's much, much more helpful. So we need implicit descriptions. Well, these lines are nicely described implicitly. This line here is where x plus y equals 1. This one is parallel, so it's x plus y equals something. Well, it's x plus y equals 5. These guys are perpendicular. They have the opposite slope. So it's where, for example, x minus y, that's going to give a line with slope 1, which this has. And we just have to plug in one of these points. X minus y, that's minus 1. And here's where x minus y is. Ooh, no, that's plus 1. Just kidding. I keep making the same error. And that's where x minus y is minus 1. Okay. So up here, we're just going to put in those things. We're going to say this first one, let's say, x plus y equals 1. How do we translate that into U and V? That's easy because I can just substitute. That's why implicit descriptions are good to go backwards with. So you just take u plus v plus u minus v equals 1. The v's happen to cancel. 2u equals 1, u equals 1/2. So let me erase this. Okay, so I'm going to put that in here as a dotted line because that's a description of this entire line and how that comes back. We don't know exactly how much of the line to use yet, but once we get all 4 lines pulled back, we'll be good. Okay, so that was one of them. Now I erase my workspace here. What about x plus y equals 5? Well, that's very similar. Okay, you add these together, you get 2u equals 5, so u equals 5 halves. Okay, and so over here at 5 halves, we get this guy. Okay. Now you might have noticed that I picked this kind of diagonal slanty rectangle. You might have thought, hey, that seems to adapt to the kind of rectangle you were showing me before. That was definitely the image of something simple over here. And I picked it exactly so that it will pull back to something simple. It's not guaranteed. If I pick some other slopes or something, this would be not as nice. If these are curves, these would be curves. But this is the kind of situation where pulling back is very nice, and the change of variables is going to be very nice. Now what about this bottom edge? X minus y equals 1. Okay, so this minus this guy, now the u's are going to cancel, and I'm going to get 2v equals 1. So v equals 1 half. Okay, that's this guy. And then I can even fit it in here. X minus y equals minus 1, this guy. Then again, when you subtract these, you plug them in, you get 2v equals minus 1, v equals minus 1 half. And so now we can finally shade in exactly what we got. So this is the mystery s, so that when we feed s in to t, we get r. Or another somewhat more sophisticated way to say it is we've calculated the pullback of r. The inverse image is another term for it, of everything that gets mapped into r by this transformation. And again, the payoff is, suppose we were integrating some function over here. This is a pain. You'd have to slice it up into different pieces. This is a much more easy integral to set up. That's not the only reason we want to understand this, but that's sort of the one of the immediate applications. So what about another example that's not linear? Not all linear functions. Well, let's do polar, because that's another pretty familiar one. But what I want to do is, for the most part, pretend that we've never heard of polar before, because we really want to get ready for some random transformations that we don't really know. So let's look at the situation here. Here's r and theta. And this is going to be a good excuse to talk about a general concept that's quite important. And we've talked about it before with linear transformations, but here it is in the nonlinear case. For example, if I have theta equals 0, well, let's push stuff forward first, and then we'll pull it back. And when we push it forward, we're going to see what's going to go on with it. Theta equals 0, for example. Let's put it in green. R equals anything. That's going to be this guy. Theta equals pi. Put that in red. Oh, let's see. Theta equals pi. What do we get? Again, we're trying to pretend we haven't heard of this before. Well, sine of pi is 0, so you get y equals 0, but x equals minus r. Okay, and that's going to go out this way. Okay, and I'm already using the fact that I mentioned before that we don't need r less than 0 here. Okay, and then one more, 2 pi. That's going to be cosine of 2 pi is 1, sine of 2 pi is 0, and then we're back to x equals r and y equals 0. Everything in the form r comma 0. And that's again back to here. Uh-oh. Now that's usually a bad thing. We've got these points and these points mapping to exactly the same. That's a very familiar thing with polar coordinates and trig in general. The fact that these guys are periodic means that you're going to get multiple addresses for everything over here. So what we usually do is we just go ahead and say, okay, I don't want anything that's going to give me multiple stuff. So the usual way to do that is theta between 0 and 2 pi, and just pick one of 0 or 2 pi. And 0 is usually simpler. Okay, so we're actually going to have this as our region. That's also the reason why we never want r less than 0 in this class, because that gives us multiple ways to address the same point. So what we've got here is that it's almost set up so that t is, I'll put a question mark, 1 to 1. Two ways to write that. So that no 2 points go to the same point here. Now, here's the annoying thing, though. Ooh, r equals 0. Every single thing on here goes to the origin. Okay, so depends on how you want to deal with that. But, you know, a good way to deal with it, if you're integrating and you're trying to find like areas and stuff or masses of lamina and all that kind of stuff, a single point's never going to matter. So you know what? For the purposes of this discussion, I'm going to say that we don't even need the origin. It's just not going to be in our set, and so I'm going to dot this as well. And now t is 1 to 1, so r is actually strictly greater than 0, just to avoid annoying things about not 1 to 1-ness. Okay, so that can be a little bit of an issue of like boundaries, special cases, places that aren't very important because they don't have very much area, and yet where things aren't one-to-one. So we're going to talk about technicalities about that later. Okay, so a little pushing forward a little bit more stuff. Let's see. If we push forward like pi over 4, theta equals pi over 4, what are we going to get? We're going to get all things of the form r times root 2 over 2, r root 2 over 2, where r is any number. So that's a curve. That's some sort of curve in the plane. X equals some r root 2 over 2, and y happens to be the same thing. Oh, well, we know what that is. It's just x equals y, stuff like that. Theta equals pi over 2. It's like this. Theta equals 3 pi over 4. It's like this. We replicate the usual part of the usual polar coordinate grid. Similarly, if r equals 1, let's see what push that forward. Okay, what do we get? Again, I'm just trying to emphasize, we just plug in. Okay, if r equals 1, we get xy equals cosine theta sine theta. That's also a parametrized curve. Now, theta is the variable, but it's all things of the form cosine theta sine theta. Well, we know that's the unit circle. That's the purpose of cosine theta and sine theta. If r equals 2, we just stick a 2 in here. 2 in here, 2 in here, and we get the standard polar coordinate grid. I want to emphasize, though, it's just by taking these functions and setting one variable to be constant and letting the other variable run and getting a parameterized curve, or setting the other variable to be constant and letting the other variable run, getting parameterized curves. In this case, they happen to be very simple curves. Okay. So let me erase that, though, and talk about going backwards. What if we had some region in x and y that we want to describe as having come from, let's put this down here, dotted, 0, 2 pi, so that's theta. We want to describe it as having come from polar coordinates. Now I'm going to, again, pick a region that is actually particularly nice in polar, and so it's going to be a little fake because we're going to sort of see automatically that's going to be nice. But I want to see how it follows from our usual stuff. So let's take this region. And suppose it's just described to me in terms of implicit equations as the boundaries are x squared plus y squared equals 4, x squared plus y squared equals 1, y equals x, that's this line, and x equals 0. Not knowing anything about polar coordinates, how would we pull that back? Well, again, we're just going to substitute these explicit descriptions in terms of r and theta into these equations. Okay, and I don't have much room. Well, let's hope we can remember those descriptions. Put the scratch up here. Okay. So, x squared plus y squared equals 4. You get r squared cosine squared theta plus r squared sine squared theta. Well, that's r squared, trig identity, equals 4. So r equals 2. It's not plus or minus because we already determined that we need r greater than 0 only to get one-to-oneness. Now, again, I always say, if we really are thinking polar, we want to recognize that shortcut. That's r squared. But we didn't have to recognize anything. We just had to know our algebra. And for a more unfamiliar transformation, it's just this process of plugging in. Okay, r equals 2. Similarly, for this guy, just exactly the same. That simplifies to r squared. That's 1. R equals 1. Okay, so we're getting very simple things in r. Okay, and then in theta, well, let's do x equals 0 first. That's a little simpler. Okay, x, remember, was r cosine theta. That's equals 0. And again, to get one-to-oneness and avoid the annoyance of r equals 0, we've assumed that r is not equal 0, so it must be that cosine theta equals 0. So theta must be, and here's a tricky bit, those are the two values that give us pi over 2 or 3 pi over 2. Okay, but look what we've got here. If theta was equal to 3 pi over 2, then we'd be down in this direction. For example, if theta was 3 pi over 2, r sine theta would be negative. That's not where we are. And so, not surprisingly, we just get theta equals pi over 2. So that's a little bit of a tricky bit. If you're not used to thinking about polar, and of course with an unfamiliar coordinate system, that would be tricky. to think about not only the equality, but that's sort of this whole line, and just to think about, well, there's these other inequalities. R squared had to be between 1 and 4, and so that tells us something a little bit more special about theta. So that's one of our lines. And then y equals x, that's r cos theta equals r sine theta. Can cancel those out. And it's cool to divide everything. Tan theta equals 1. You don't have to do it that way. It's just where cosine theta and sine theta are the same. Again, we get two answers, but only one of them really is relevant, because we know that x and y have to be positive in this region. If we have theta equals this and r is positive, we're not going to get positive numbers from r cosine theta and r sine theta. So we can x that out, and we get pi over 4. So it's this guy. Okay, so that's a very explicit description. And of course, we could have done that much quicker with our intuition about polar, but I wanted to show you how it follows from the general procedure of plugging in the transformation equations into these implicit descriptions of the boundaries of the region.